Today I'm going to work through a few more Dirichlet problems in polar coordinates. So we're going to have the same equation that we were working with before, that the Laplacian of u, which in polar coordinates is u sub r plus 1 over r u sub r plus 1 over r squared u sub theta theta equals 0. But instead of a circular domain, we will be looking at an annulus. So think about an inner circle of radius alpha and an outer circle of radius beta. Pretend those are circles. Okay, so we're going to specify the value of the function as a function of theta on the inner circle, and then the value of the function as a function of theta on the outer circle. And that will be the boundary value problem that we want to solve. We're going to again assume that our function must have a period of 2 pi. Now, we already did the separation of variables for Laplace's equation in polar coordinates. So we just have that theta double prime plus lambda theta equals 0 is our first problem, and r squared r double prime of r plus r prime of r plus lambda r of r is equal to 0 as our second problem. Last time we solved the first problem, we saw that if lambda is equal to 0, then our only eigenfunction is 1. But if lambda is bigger than 0, then our eigenfunctions are of the form c1 cosine of n theta plus c2 sine of n theta, where the eigenvalues are lambda sub n equals n squared. And then we were able to solve the Euler type equation. So r squared r double prime of r plus r prime of r plus lambda, which in this case is n squared, r of r is equal to 0. We saw that in the n equals 0 case, that r sub 0 of r was a0 plus b0 natural log of r. And we saw for the n greater than or equal to 0 case that r sub n is supposed to be of the form a sub n r to the n plus b sub n r to the minus n. So we don't have those conditions that we had before that got rid of terms like natural log of r or r to the minus n, because we are working on a finite domain, and we don't have to worry about what happens as r goes to 0. So the general solution is quite lengthy. It's going to be a0 plus b0 natural log of r plus the sum from n equals 1 to infinity of a sub n r to the n plus b sub n r to the minus n, all of that times cosine of n theta. And then we'll have similar terms. We'll call them c sub n r to the n plus d sub n r to the minus n, and those will multiply sine n theta. And so these a sub n, b sub n, c sub n, d sub n are really taking the place of the constants c1, c2, or the a sub n and b sub n that you see there. Now, so what we have to do is figure out the coefficients a sub 0, b sub 0, a sub n, b sub n, c sub n, and d sub n. So we do that by applying the, I can't believe this is still there, boundary conditions. And by applying the boundary conditions, we should have that f of theta, which is u of the inner radius alpha theta, is equal to a sub 0 plus b sub 0 natural log of alpha, the inner radius, plus the sum from n equals 1 to infinity of a sub n alpha to the n plus b sub n alpha to the minus n cosine n theta plus c sub n alpha to the n plus d sub n alpha to the minus n sine of n theta. Now g of theta will be u of beta theta, the outer radius, which is again a sub 0 plus b sub 0 natural log of beta, plus the sum from n equals 1 to infinity of a sub n beta to the n plus b sub n beta to the minus n cosine of n theta plus c sub n beta to the n plus d sub n beta to the minus n sine of n theta. And so both of the terms that you see there from the boundary conditions are Fourier series. Because they are Fourier series, we should be able to use that information to figure out what the coefficients are. So the first thing that we would see is that a sub 0 plus b sub 0 natural log of alpha, that's the constant term, so that should be 1 over 2 pi times the integral from 0 to 2 pi of f of theta d theta, which is the average value of f. Okay, so the constant in that first boundary condition that we applied is going to be the average value of f. The constant in the second boundary condition that we applied is going to be the coefficient, or the average value of g. So 1 over 2 pi, the integral from 0 to 2 pi of g of theta d theta. Then we're going to want to move on, okay, to the coefficients a sub n and b sub n. You'll see that they appear in the first boundary condition and second boundary condition as coefficients of cosine of n theta. So a sub n, I'm going to move this up here. So a sub n plus alpha to the n plus b sub n alpha to the minus n is going to be our familiar coefficient for the cosines, the integral from 0 to 2 pi of f of theta sine, sorry, it's not sine, cosine of n theta d theta. And then a sub n beta to the n plus b sub n beta to the minus n is going to be our familiar coefficient of cosine, 1 over 2 pi, the integral from 0 to 2 pi g of theta cosine of n theta d theta. Okay, so I really want you to see that the f of theta here with the alpha of the n, or a sub n alpha of the n plus b sub n alpha of the n minus n, is really matching with this piece in the cosine n theta. Okay, maybe I'll change colors here. Okay, then we have the a sub n beta to the n plus b sub n beta to the minus n with the cosine n theta. Okay, that's going to match this piece right there. Okay, so now similarly, we're going to want to get the c sub n's and the d sub n's. Those are going to be 1 over 2 pi integral from 0 to 2 pi of f of theta sine of n theta d theta, and 1 over 2 pi integral from 0 to 2 pi g of theta sine of n theta d theta. Okay, so again, we're matching these c sub n's with the sine n thetas. Okay, those come from this part right there. Okay, and then picking another color. Okay, so then the coefficients of sine n theta in the second equation, right, those are going to match these beta terms right there. So this becomes a fairly difficult process to follow in order to do some of the examples. And so we're going to do the very simplest of examples in class tomorrow. So I'm actually going to move on to another problem and leave the examples that you see below here to do tomorrow in class. So I want to move on to a second problem that we did not solve last time, which is the exterior Dirichlet problem. So we're going to look at, imagine that we have a circle here, and what we're interested in is what is the value of u outside of this circle. Okay, so that circle, I'm going to give a radius a, okay, and we're going to specify the value of f of theta around that circle a, and then what I'm really interested in is going to be the value of u, okay, outside, for radiuses outside of that blue circle of radius a. Okay, so again, most of this problem is going to be exactly the same, so I'm not going to go through all the steps to solve it. Okay, from the previous problem, we still, that we worked on before, we do have that, that theta sub 0 is just the constant 1. So this is similar to when we were working with the inside inside of the circle, okay, or with the annulus that we did before. We also have that theta sub n of theta is just c sub n cosine plus d sub n sine of n theta, okay? And then just like the examples that we had last time, we have r sub 0, which is a sub 0 plus b sub 0 natural log of r. And then we have r sub n, which is a sub n r to the minus n plus, wow, yeah, a sub n r to the minus n plus b sub n r to the n. Okay. Additionally, in order to make this problem work, we're going to have to assume that as r goes to infinity, that u of r theta has to go to 0. So we don't want this function to go get larger and larger as you go to infinity. Okay. What that does is that gets rid of the b sub n's. Okay. If you take the limit as r goes to infinity, natural log of r would go to infinity, so we don't want that. Okay, and r to the n, when it's a positive n, would go to infinity, so we don't want that. So we're just left with the a sub 0 term and the a sub n r to the minus n terms. Okay, so the general solution is going to be, we'll just put it as c sub 0 plus the sum from n equals 1 to infinity. And what are the terms going to look like? They're going to be the r of r times the theta of theta. So this is going to be r to the minus n's, okay, times things that look like c sub n cosine of n theta and d sub n sine of n theta. And what you should notice is that these coefficients a sub n I've kind of absorbed into the c sub n's and the d sub n's. Okay, so how do we get the coefficients? Well, for the c sub 0, right, we're going to do the average value of f of theta, so 1 over 2 pi, integral from 0 to 2 pi of f of theta d theta. The coefficients of the cosines, okay, so the coefficients of the cosines we're going to want to do an integral from 0 to 2 pi of f of theta cosine of n theta d theta. Okay, that's going to have a 1 over pi on the outside. But the coefficient of cosine, you'll see, is going to be a to the minus n times c sub n. Okay, so c sub n, and then we're going to plug in the radius a there. So we're going to multiply that to the other side, so we get a positive a to the n there. So c sub n is going to be a to the n over pi times our standard integral from 0 to 2 pi of f of theta cosine n theta d theta. Okay, and if we use a similar logic, then we get a to the n over pi times the integral from 0 to 2 pi of f of theta times sine of n theta d theta. And so if you compare this to what we had gotten for the circle before, previously we had had that the a sub n's were on the bottom, okay, now that they're on the top, okay, and then previously we had r to the positive n, okay, now that we're looking at the outside of the circle, we're going to have r to the minus n. And that's how you would solve the exterior Dirichlet problem. And we will do more examples with these in class tomorrow.